Please excuse my dear Aunt Sally. People eat more donuts after school? Peanuts ended my donut addiction Saturday. What? Pink emus marching down a street. Who came up with these things? Purple eggplants make delicious afternoon snacks. Okay, that's where I draw the line. Which one of you made me say such disgusting things? I mean, who eats purple eggplants? Vegetarian? Oh, well, then I guess we shouldn't offend that demographic. This one's my personal favorite. Purple elephants must destroy a school. Maybe they use snot rocket launchers. What's that? What do you mean it's not funny? PEMDAS, that great acronym that tells us how to do arithmetic and causes all sorts of mathematical drama on Facebook.
Oh, I weep for humanity.
We've used PEMDAS to teach students the order of operations for decades. It's sort of a benchmark of arithmetic education. To master it makes for a fun party game to show how old calculators mess it up. It's a merit badge of mathematical competence to the Facebook crowd and basic prerequisite knowledge for college algebra courses. It's also a lie. To understand what I mean, we first need to talk about what PEMDAS really stands for instead of those awesome mnemonic acronyms. PEMDAS stands for
Parentheses, exponents, multiplication, division, addition, and subtraction.
The order of operations is designed to make it clear how to communicate a certain arithmetic operation to another person. Just like how language requires good grammar to make sentences mean the same thing to different people, mathematics requires good grammar too. Just check out anyone arguing about the Oxford comma to see how important grammar can be in communicating an idea, or heck, any comma at all. I mean, just listen to the differences here between
Let's eat, Grandma, and let's eat, Grandma.
I mean, one of these is a fine invitation to dinner, while the other is a horrific flashback to the Red Riding Hood nightmare. And all because of one tiny comma. And that idea wasn't anywhere near as complicated as something mathematical. In fact, because the ideas that mathematics is designed to express are so precise, using correct grammar in mathematics is literally way more important than it is in regular language. And yes, to all you grammar nags out there, I literally meant literally.
Take, for example, the expression 2 plus 3 times 4. See, the problem here is that all arithmetic operations are binary operations, which means that they take exactly two numbers to do something. Here we are trying to combine three numbers, so which two we combine first matters, as combining in a different order might lead to something else and make this expression mean something different. Here one reader might read from left to right and combine the 2 plus 3 first to get 5, and then times by 4 to get 20. On the other hand, another reader might combine the 3 times 4 first to get 12, and then add 2 to get 14. Right now, it's less important which one is right than the fact that they got two answers. This means that this expression is ambiguous, which makes it useless in communicating information. What if the writer meant for it to mean 20 and the reader interpreted it as 14? This is why it is important for us to agree about which operations occur first. In this case, we have agreed that because multiplication means iterated addition, that is, a lot of successive additions, that multiplication always occurs before addition in any written calculation, regardless of whether the addition is written to the left or not. Thus, in this case, the correct answer is 14.
And that's what PEMDAS is all about. It tells us what the agreed upon order is in doing arithmetic. Exponents occur before multiplication, which occurs before addition. But what about addition and subtraction? According to the order in PEMDAS, addition should occur first. But is this always true?
Consider 3 minus 5 plus 4. According to PEMDAS, the addition occurs first, and we get 5 plus 4 is 9, and 3 minus 9 is negative 6. On the other hand, going from left to right yields 3 minus 5 is negative 2, and negative 2 plus 4 is 2.
What the formula?
So which is right? I mean, you would think we should go with the order of operations, and the answer is negative 6. But it's not. The answer is actually 2.
I'm not saying it again. So what is going on here? Well, this is where the lie about PEMDAS starts to come in. See, when it comes to addition and subtraction, instead of doing addition first and subtraction second, you're supposed to do them from the left to the right. Does that seem arbitrary to anyone else? To do this right, you have to remember some weird rule that's different than what the mnemonic is supposed to help us remember. At least with multiplication and addition, there was a reason. Multiplication is a bunch of additions packed together, and it changes which things are being added if we don't do it first. But here it's like addition and subtraction are on the same level, and we just tell you to do them from left to right, even though we list addition first. But why left to right? Why not right to left? Wouldn't that be just as reasonable? Actually, the reason why we go from left to right is much deeper and reveals an even greater lie about arithmetic. Okay, so I didn't want to say this in earshot of anyone, as it may be a little bit of a shock and maybe disturbing to our younger viewers, but subtraction is not a real operation. All right, that requires a little bit of an explanation. See, subtraction does mean what you think it means. It's what we call taking away a certain number of things from another number. What I mean by saying that subtraction is not a real operation is that it's actually shorthand for doing the operation addition with certain kinds of numbers. Take, for example, 7 minus 3. The minus sign here is actually shorthand for add the negative of the number immediately to my right. That is, 7 minus 3 is really 7 plus negative 3, which produces the result 4 as expected. So subtraction is really addition, and that's why it occurs at the same time as addition. But if you look closely, you can also see why we have to do addition and subtraction from left to right. It's actually the subtraction's fault. The subtraction shorthand says to do something to the number to its right. That means that for that expression to ever have a hope of meaning the same thing to different people who may rearrange the order or add them in different ways, that minus sign has to stay glued to that number, and you can't do anything to that number without the sign. The easiest way for a teacher to make sure that happens without explaining all this is to tell you to always do subtraction and addition from left to right. But all of that confusedness goes away if we just resolve the shorthand first and then do the arithmetic. Let's see what happens when we apply it to our expression before. Here, the 3 minus 5 resolves into 3 plus negative 5. From here, it doesn't matter which order we do these additions in, as addition is what we call associative. If you don't know what the associative property of addition is, there's a link down in the description, but it basically means that when you have a string of all additions, it doesn't matter in which order you add the numbers. And sure enough, if we do the first addition first, we get 3 plus negative 5, which is negative 2, plus the 4 is 2. And doing the second addition first, we get negative 5 plus 4 is negative 1, plus the 3 is 2. All the ambiguity is gone. Everyone agrees on what the expression means as long as we resolve the subtractions first. So as long as we resolve the subtraction shorthand first, the order of operation is really just PEMDA at this point. But the fun doesn't end there. It turns out that there is something similarly fishy with multiplication and division. Consider 5 divided by 10 times 2. According to PEMDAS, the multiplication occurs first, and we get 10 times 2 is 20, and 5 divided by 20 is 1/4. On the other hand, going from left to right yields 5 divided by 10 is 1/2 times 2 is 1. What, the formula? Wait, didn't we already do this gag? So here again, which one is right? Like before, we might think that we should go with the order of operations, and the answer is 1/4. But also, like before, it's not. The answer is actually 1. I'm telling you, we already did this. What's interesting is the same thing that's supposed to happen with addition and subtraction happens here too. You're supposed to do the multiplication and division at the same time and resolve them as you move from left to right. So again, PEMDAS is lying about their order. And like before, this is to cover up yet another lie about arithmetic. Division is not a real operation either. Oh, where's that door? Ow! As you might expect at this point, division still means what you think it means. It's what we call breaking up a collection of things into a certain number of smaller subcollections and identifying how much is in each subcollection. But like subtraction before, division is also shorthand for something. In this case, it's shorthand for doing the operation multiplication with certain kinds of numbers.
Take, for example, 12 divided by 4. The division sign here is actually shorthand for multiply by the reciprocal of the number immediately to my right. That is, 12 divided by 4 is really 12 times 1/4, which produces the result 3, as expected. So division is really multiplication, and that's why it occurs at the same time as multiplication. But we end up doing them from left to right for basically the same reason we did addition and subtraction from left to right. In this case, it's the division's fault. The division shorthand says to do something to the number to its right. That means that for that expression to mean the same thing to different people who may rearrange the order or add them in different ways, that division sign has to stay glued to that number, and you can't do anything to that number without the division sign. And just like before, the easiest way for a teacher to make sure that happens without explaining all this is to tell you to always do division and multiplication from left to right. But again, like before, if we just resolve the shorthand first and then do the arithmetic, all that perplexity goes away. Let's see what happens when we apply it to our expression before. Here, the 5 divided by 10 resolves into 5 times 1/10. From here, it doesn't matter which order we do these multiplications in, as multiplication is also associative like addition. And sure enough, if we do the first multiplication first, we get 5 times 1/10 is 1/2 times the 2 is 1. And doing the second multiplication first, we get 1/10 times 2 is 1/5 times 5 is 1. Again, all the ambiguity is gone. Everyone agrees on what the expression means as long as we resolve the divisions first.
This exact meaning of multiplication has come up for you before. When dividing two fractions, you always flip the one on the right and multiply. That always seemed a little odd to me and out of left field, but as you can see from what we just did, it's actually just the definition of division at work.
See, when we divide 3/5 by 4/7, we recognize that the division is shorthand for multiply by the reciprocal of the number to my right. And this turns this into 3/5 times 7/4. Not because of some weird out of nowhere rule, but because that's literally what division means.
Since division is really shorthand for multiplication by the reciprocal, like before, as long as we resolve all the division shorthand first, we can eliminate another letter from the order of operations and get PIMA. Now, while this may sound like FEMA's nerdy younger sister, it really makes a lot more sense now. PIMA stands for parentheses, exponents, multiplication, and addition. This is the order because multiplication is simply grouped up addition. 3 times 4 is really 3 plus 3 plus 3 plus 3 as a group, as if it's in parentheses. Similarly, exponents are simply grouped up multiplication. 5 to the third power is really 5 times 5 times 5 as a group, again as if it's in parentheses. The parentheses allow us a way of artificially prioritizing any computation over the others. Because of this, we now have a complete ability to communicate a complex expression's value to someone else in a way that everyone will agree with the meaning.
As a last example, consider 3 minus 6 times 3 plus 2 cubed divided by the quantity 3 plus 1. According to PIMA, we should resolve the parentheses first, so we add the 3 plus 1 together to get 4, and update 3 minus 6 times 3 plus 2 cubed divided by 4. Then we resolve the exponent next. 2 cubed is 8, so we update again to get 3 minus 6 times 3 plus 8 divided by 4. Then we get to the multiplication step. But here we resolve the division and subtraction shorthands first to get 3 plus negative 6 times 3 plus 8 times 1/4. Then we resolve the two multiplications in either order. Negative 6 times 3 is negative 18, and 8 times 1/4 is 8/4, or 2. Updating yields 3 plus negative 18 plus 2. Now that everything is addition, we can add in any order. But in this case, if we start at 3 and then add negative 18, which means to go left on a number line 18 steps, we get negative 15. Adding 2, meaning we go right on a number line 2 steps, yields negative 13 as the answer. In fact, if you have a calculator that allows you to enter a complete line of arithmetic before resolving anything, you'll get negative 13. However, a 4-function calculator would get this wrong because it evaluates everything you hit as a new operation. So when you put this in from left to right into a 4-function calculator and it evaluates as you go, it is really putting in a parentheses every time you hit an operation, since that will force evaluation each time, which really means it's evaluating this expression, which we know from the order of operations means something very, very different. Think of that the next time you see a Facebook post like this and someone tries to use a calculator to justify a wrong answer.
So why do we teach subtraction and division the way we do and cause weird ambiguities and seemingly arbitrary rules in things like PEMDAS? I think it's because many educators are frightened that young students might not be able to cope with a negative number or the idea of a reciprocal. But just like the usual 4 operations, there are very natural ways in which even younger kids use negative numbers and reciprocals. Like how a negative number really just means to move left or backwards. I mean, how many board games do that? Perhaps what we really need to do is just connect them to the natural ideas better. But that's a subject for another time. I hope you enjoyed looking at what the order of operations is all about with me today, and why it's important if we want to communicate complicated quantitative ideas effectively. And hopefully we resolve some of the mysterious ambiguities it has. If you like this video, consider watching one of my other videos. And don't forget to drop a like and subscribe. We'll see you next time on Philomath Party.